Live, and this stream sadly won't be as long as my normal ones, Monday, Wednesday, Friday. But honestly, today has been a crazy one. I set my alarm to be a bit earlier. Audio seems to be working. Actually, audio does not, or video does not seem to be working. So I will again reset my video, and we should be good to go. Audio is good to go. And hello, everybody. My name I'm Chloe, and welcome to Smoothie with Chloe in the morning. I'm actually going to also just make sure the door is actually closed in the room here, just to make sure we don't get any extra sounds coming in, hopefully. But the door also doesn't work that well. Hope everyone's having a wonderful week. So over the past week or so, and for the next, I guess, couple of months, I hope, I'm going to be going through this textbook, Cryptography Engineering, and we're hoping to have a study group for it as well, starting soon. So the study group will be happening in the Uncloak Discord. Down here, you'll see there's a study group. The text, here covering, what the assignments, what's going to happen. So I am not an expert in any shape, form, or way. But I do feel as though a lot of this information is important for those wanting to learn to be practical cryptography engineers. And so we're trying to kind of, from my point of view, create a community around learning. And so highest level and lowest barrier to entry is just reading the text. Just trying to make sense of it and just reading through every word, reading through every diagram, and that's what I'm doing here on these live streams. I also do it, once, usually on my mobile device in the morning, so I already read for about an hour or so this morning. Now I'm going to read for about half an hour or so live, just to kind of make sure I get some notes down and just kind of to keep track of my note taking, and then also there's in the afternoons I'm going to start going through the examples. Actually, I'm going to write that whole thing down, and then it's also going to want me to put an actual title here. So maybe I can put a nice little H1, so we get an actual title, and here we go. So hopefully, I did the same thing here, so getting used to Obsidian. So this is the title of the actual book, but I think I also need a title of the actual, notes on the text, I think, because I'm pretty sure this is just the title of the actual note or text file. So I've been taking notes here on Obsidian, getting used to the note taker. Habitually, I used HackMD, but even then, I only used HackMD for about 3 or 4 months. So, gonna stop with the introduction now and kind of just get into the text. If this is definitely just for me, but if you happen to follow along and find this video and you're into cryptography engineering, that is what I'm reading about. And we're starting off with Kirchhoff's principle. So Bob needs 2 things to decrypt the ciphertext. And so you have the plain text and you have the ciphertext, which has been encrypted, which is an encrypted message. Bob, so he must know the decryption algorithm, D, and the key, K. So this is from the diagram above, to be able to decrypt the ciphertext here. Bob must know the decryption algorithm, D. So this is like the function, with these, these variables are going to go into, so the function. And the key, right? The key for this certain encryption algorithm. An important rule is Kirchhoff's principle. So just to get it, the security of the encryption scheme must depend only on the security of the key. And I'm going to try and do this again. Key lower e, I think should be that. And so yeah, it always takes me a little while to get the latex down for the first time. So latex is just, how you make numbers look all fancy and how you like put things to like the exponent or whatever. Oops. Yeah, that didn't even look. Oh, sorry. The exponent of 3. But it takes a while to get used to. I like that Obsidian shows the latex right away, like in the editor, which is super cool, so I can know if I made a mistake. I think with HackMD, I used to have something on the side, like 2 screens. And not the security of the algorithm. So the security of an encryption scheme must depend only on the security of the key and not the security of the algorithm. There are good reasons for this rule. So, what are some of them? Algorithms are hard to change. So they are built into software or hardware, which can be difficult to update. So I think that's a pretty valid point overall. Algos are to change, built into software, hardware, In practical situations, the same algorithm is used for a long time. That is just a fact of life. So even like, taking things, I'm going to try and take most of this back to like, blockchain or crypto or just, general examples that I understand at least. But for the marmaj gaming DAO, we have certain algorithms that we use for, dispensing NFTs or game items or even, rewards, economic rewards. And so the algorithm isn't something that we want to go in and change all the time, but the way people interact with it, there's cryptography for that, should be secure regardless. That's how I see it, at least, in a very simple sense, not even thinking about cryptography and just, abstracting to algorithms in general. It is hard enough to keep a simple key secret, now going into like crypto. Keeping the algorithm secret is far more difficult and therefore more expensive. Nobody builds a cryptographic system hard enough to keep. I think this is a good like mental image too. Keep a key secret more difficult, right? And more expensive to keep algo secret. Nobody builds a cryptographic system for just 2 users. Every participant in the system, and there could be millions, or billions, I guess, uses the same algorithm. Eve would only have to get the algorithm from one of them, and one of them is bound to be easy to subvert. Or she could just steal a laptop with the algorithm on it, and remember our paranoia model. Eve might very well be one of the other users of the system, or even one of its designers. I guess that's obviously an issue if the designer or whatever. There are also good reasons why algorithms should be published. So there are some protocols that have, private algorithms, of course. But, saying here, from experience, we know that it is very easy to make a small mistake and create a cryptographic algorithm that is weak. If the algorithm isn't public, nobody will find this fault until the attacker tries to attack it. The attacker can then use the flaw to break the system. We have analyzed quite a number of secret encryption algorithms, and all of them had weaknesses. This is why there is a healthy distrust of proprietary, confidential, or otherwise secret algorithms. This, to me, was an interesting point. So, just like, I don't know if it's like, the authors of this book analyzed, quite a number, whatever that number is, of secret encryption goes. Why did I? I'm going to add that to the dictionary because I'm definitely going to write that 1,000 more times. And I think that's insane. All of them had flaws. I mean, okay, maybe they're not perfect, but so it seems like there's area for improvement in every single area if every single protocol had weaknesses that they tested. This is why there is a healthy distrust of proprietary, confidential, or otherwise secret algorithms. Don't be fooled by the old, well, if we keep the algo secret too, it will only increase security. So security by obscurity. Don't trust security by obscurity. That's how I take that, at least. That's supposed to be 5. There we go. I think so, right? And then 2. What am I doing? 0.1s. Get 3. Sorry, I'm just forgetting how I'm taking my notes already. I thought I meant to do it like that, though. Top 1, 3, and then I made this one a 2. Okay, yeah, I guess I did do it like this. 2, 3, 4. I guess I didn't use 5s in this one. Oh, they don't show up, that's why. Haha, sorry. A little tangent for me. 2.2. Authentication. I should probably put the authors and everything. Oh, I think I spelled that wrong. Kirchhoff. Yeah. I can't copy and paste here, but I'm sure there's some program I can use to screenshot this and put it into some text, but that's boring too. Typing it out will help me remember, probably. So, besides, Bob and Alice have another problem. In figure 2.1, Eve can do more than just listen in on the message. Eve can also change the message in some way. So Eve, malicious. Oh my gosh. Who is malicious? Can do more than just listen. They can also change the message in some way. So M is transformed into. Does this work? M prime. There you go. And I think I could actually, sorry. There you go. So message will turn into message. Okay. This requires Eve to have a bit more control over the communication channel, but that is not at all an impossibility. For example, in figure 2.3. So I'm just going to keep this simple. Oh, gosh. Whew. I was really tired today. But, I mean, probably my fault, like, 99%. Because, like, whoops. It said selection, my friend. Okay. This seems like the simplest way to create a nice little table. And then I can copy it and obviously save it, but then paste it. Ha 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 ha. It makes it so simple. That came out a little blurry, but oh, that came out really blurry, didn't it? Let's see. My screen's also very small. Oh no, it came out fine. My screen was just really small. Okay. Oh, sorry. I will write... Can I write in the name of the image? Like an alias? Type to change display text. Fig 2.3? It didn't work. I'm not amazing with Obsidian yet. I thought I'd be able to just... Does it have to go here? Nope, doesn't like that. Could just write, of course, but I think there's a way to actually have it just, you know. I guess I'll write the caption too. So, how does Bob know who sent the message? So that's the kind of the question. If Eve is able to change out so Alice is trying to send a message to Bob. If Eve is able to change out the message, how does Bob really know that Eve sent the message? So Eve needs more control to do that. So this is kind of what's happening here. But Eve interferes with the communication channel. Instead of receiving M, Bob receives a different message, you know, M prime. We assume that Eve also learns the contents of the message M that Alice tried to send. So Eve also knows what Alice tried to send. So even worse, Eve can be like, oh, you tried to send, you know, how was your day? And then Eve can be like, okay, well, I'll send that same thing plus some extra information to try and get something out of Bob and read that message back. So how do you stop that, I guess, is the question of authentication. Other things that Eve could do are delete a message so that Bob never sees it, insert a new message that she invents, record a message, and then send it to Bob later, or change the order of the messages. So Eve could pretty much, in this situation, do whatever they want with the messages, for the most part, it seems like. Allow them to go, not allow them to go, read them, change the order. So I guess in this situation, like, yeah, anyways. Consider the point in the process where Bob has just received a message. Why should Bob believe the message came from Alice? He has no reason to think it did. And if he doesn't know who sent the message, then the message is pretty useless. Okay. To resolve this problem, we introduce authentication. Like encryption, so I think that's like a part that would be helpful for most people, or for me at least. Encryption authentication uses a secret key that Alice and Bob both know. And this key is sorry, the authentication key, which is different than the encryption key, which has a little E at the bottom. But they're both keys, so lengths of, you know, bits, bytes, all that good stuff. We'll call the authentication key KA. Figure 2.4 shows the process of authenticating a message M. So first we were encrypting a message, M, to make sure that the message details weren't in plain text, right? So the message is in ciphertext, so you can't just read it easily. You need some sort of encryption scheme. But then if Eve finds the message, they can at least read the encryption or read the message the way it is encrypted, the ciphertext, change it, whatever else. So you also want to make sure Bob knows, because if Eve might, anyways, doesn't even matter. The point is, this is how we're going to use authentication. When Alice sends a message M, okay, so Alice is sending the message to Bob just like before. She computes a message authentication code, or a MAC. Okay, so it might, the message is the authentication, which is going to be all this good stuff. MAC A. Okay, so the A, such as A is H, KA with M. And then H is the MAC function. Okay, so it's usually, always have some sort of function with these kind of arguments. Is the authentication key. So that seems useful. Alice computes the MAC. Yeah, I'll write that. Alice computes the MAC A as, okay, let's see how I do here. Equals H. This should be relatively easy, I think. Nope. H bracket K underscore A dash M bracket. It did work. And I wonder if I should just leave this all together so it all looks like one math equation. Doesn't look bad. Maybe I should have it on one line. Yeah, it looks better like that for sure. Okay. That looks pretty good, I think. HK. Yeah. That looks good. Where H is the MAC function, which we know, and we already know this as well, but it doesn't hurt to kind of, in my opinion, to repeat things to make sure that they're understood. Is the authentication key. So this should be relatively clear because M we know is the message, right? And so you have the MAC function H, the authentication key, and so you obviously with the function with these two parameters input into the function, you'd be able to get the MAC authentication code. Sorry, message authentication code. Okay, Alice now sends both M and A to Bob. So, that part is also shown in the diagram. So the key doesn't get sent, but that seems like Alice. M and A to Bob. What else? When Bob receives M and A, he recomputes what A should have been using the key that Bob has, right? Eve doesn't have this key. Bob has his authentication key. Just like before, Eve didn't have the encryption key. Bob has. So up like before, where was it? Like this one. There's a key KE with Alice and a KE with Bob and no KE with Eve. It's a similar type of situation. Okay, so Bob receives, or we know Bob receives it, so let's just leave that. He recomputes A using KA and checks to see if received A is correct. So Bob's able to do that because Bob has the authentication key. And I will just... Okay, I might be a weirdo, but I like figures on top of the explanation. My brain likes looking at the explanation and trying to figure it out, and then coming back to like read it and be like, oh, that was right, or oh, that was wrong. Whenever I read through an explanation first, I get a little bit confused. It's almost like it's too easy, you know? Not too easy, but like I want to do some mental work first. Generic setting for off. This one still looks weird, even though it's... I gotta start taking the pictures smaller? I don't know, man. Doesn't matter. It's good enough. So now Eve wants to modify the message M to a different message M prime. If she simply replaces M with M prime, Bob will still compute, right? So Alice is trying to send M and A. But if Eve replaces M, and now you have M prime, when Bob computes this H function, the A will be different because it's not M, it's M prime. And so he'll know that the A is different, like it's different than what Alice had. So the authentication key won't match what Alice was giving out. If you simply Bob will still compute and compare it to A, but a good Mac function will not give the same result. So I guess I'll put that part. A good Mac function will not give the same result for H. I mean, this is relatively, again, straightforward, but I think seeing it like this, for me at least, is what clarifies what's happening. I have like 10 more minutes, but I hopefully will be able to get through a little more of this. It's been taking me a little while recently. Okay, so good Mac function will not give the same result for those two different messages. So Bob will recognize that the message is not correct. Given that the message is wrong in one way or another, Bob will just discard the message, right? So, you know, if A is okay, so there is, okay, I'm just going to not go too deep into things because it does explain it pretty well. Okay, so if we assume that Eve does not know the authentication key, the only way Eve can get a message and a valid Mac key is to listen to Alice when she sends messages to Bob. This still allows Eve to try some mischief. So I think that's kind of the important part here. So Eve can, listen to Alice as she sends messages to record a simple, so Eve can record messages and their max and then replay them by sending them to Bob at any later time. So again, if Alice is sending the MAC and I need to know this MAC value or whatever, this A value, okay, well, I'll just listen to Alice and then I'll know the A value, then I can use it later. Maybe keep it really simple, right? Pure authentication is only a partial solution. Eve can still delete messages. Remember that Alice sends. She can also repeat old messages or change the message's order. Therefore, authentication is almost always combined with a numbering scheme, like in blockchains, like a nonce, or not in just blockchains. I guess a nonce is outside of blockchains too, so just a nonce. To number the messages sequentially. So authentication is only part of the solution. I think it was pretty good just to have like a list of like why. Eve can still repeat old messages. Oops, sorry. I like keeping things in somewhat order. Delete messages from Alice. Bob. Repeat old messages. Or change message order. I'll just be like, usually combined with numbering notes. Alright, because of those issues, I guess. Yep. So if M contains such a message number, then Bob is not fooled by Eve when she replays old messages. Because again, I have a message with the number 10 from Alice already. So if Eve tries to replay that message with that number, I'll be like, nope, I already got number 10. I have that ticked off in my list, in my table or whatever. Bob is not fooled by Eve when she replays old messages. Bob will simply see that the message has a correct MAC, but the sequence number is that of an old message, so he will discard it. So there you go. I mean, that's simple enough in my opinion. So, authentication is in combination with message numbering solves most of the problem. Eve can still stop Alice and Bob from communicating or delay messages by first deleting them and then sending them to Bob at a later time. But Bob still gets the message only once, and it's the exact same message that Alice intended. So that's the positive there. If the messages aren't also encrypted, so if Eve can actually see the message, the message text, the plain text, then Eve can selectively delete or delay messages based on their content. But deleting or delaying messages is about the extent of what she can do. So basically saying, like, if you could know, like on blockchains, you have MEV, you see messages, you're able to change the message order. That is something that some people would find to be a negative. But if you're able to, for example, hash all the transactions or put them through some cryptographic scheme, then you'd be able to have the transactions be private. The problem with that is if that was all private, you'd increase latency. And then you still have to have someone choose the order of the block and read the messages. So, yeah. But anyways. You could have less people choose or whatever, but it doesn't really matter. The best way to look at it is to consider the case where Alice sends a sequence of messages M1, M2, M3. Bob only accepts messages with a proper MAC, okay, so with a proper authentication code, and whose number is strictly greater. So, you know, the nonce needs to increment. And you could have some, you know, anyways. Then the message number, the last message he accepted. So Bob receives a sequence of messages that is a subsequence of the sequence that Alice sent. A subsequence is simply the same sequence with 0 or more messages deleted. This is the extent of which cryptography can help in this situation. Bob will receive a subsequence of the messages that Alice sent, but other than deleting certain messages or stopping all communications, Eve cannot manipulate the message traffic. To avoid the loss of information, Alice and Bob will often use a scheme of resending messages that were lost. But that is more application specific and not a part of the cryptography. So that's kind of talking about how, you know, if Alice and Bob are sending messages back and forth, and let's say, you know, because of Eve or because of whatever other reason, a message got deleted by Bob because maybe Alice sent it incorrectly or Eve tried to maliciously intercept and it got deleted. The application can like retry and get the message from Alice, or like your email server might like, you know, try and get old emails back that weren't sent or whatever. But that's application specific, not cryptography specific. Of course, in many situations, Alice and Bob will want to use both encryption and authentication, which I think is most of the cases. We will discuss this combination in great detail later. Never confuse the two concepts. Encrypting a message does not stop manipulation of its contents. Okay, so and authenticating a message doesn't keep the message secret. So I think like Telegram's a good example of like, it'll authenticate that a message went to somebody, or if they received it, but the messages aren't encrypted by nature. Whereas like Signal, for example, everyone's always talking about how Signal's potentially better because there's encryption built into the algorithm. Let's see, I don't think there's enough time for me to really dig into much of this at all. Wow, today took a while. But I will set up public key encryption. I'll just write these two last points down just to make it clear. So, encrypting a, well, could just put E of M, but let's see. Gotta practice anyway. What letter do they use for the encryption function? Yeah, they just use F. So doesn't so encrypting the message doesn't stop manipulation of contents. They used H, but I don't think it was a capital. I think we're supposed to use a lowercase f. Anyways, and then I'll use H just so that I think they wanted to keep it different. And if you authenticate a message, doesn't keep a message secret. Okay. So hopefully this is simple. If you encrypt a message, that's what this little E symbol stands for, it doesn't stop someone from changing its contents. You can't read the contents, you can't know what the contents are, but you could still change them on the way to Bob. And Bob just goes, okay, sure, like this is what I'm supposed to get. Authentication, making sure that Bob knows that this came from Alice, doesn't keep the message secret. Now, if you want a secret message that you know came from Alice, you need both, which makes sense. Okay, uno, dos, tres, 2.3, public key encryption. So yeah, the first two chapters honestly are very introductory and very basic. Chapter 3 just goes from 0 to like 50 and gets quite a bit more difficult with like bringing in some math concepts and some programming concepts, which I'm actually excited for. So I'm probably going to have like a terminal open as well soon to the left here. And you can see I have my reading on the right, my notes in the middle, and then probably terminal on the left. For now, at least, and this is probably going to change a lot over the next couple of months. I'm honestly just trying to get a setup back and going again to get more efficient research. So when I get to the questions, so the one thing I didn't do today, actually, which I kind of want to do, I'm not going to go through the security review exercises, but I am going to like, so okay, so we did this. Oops. And it's kind of awkward, but 1.13. Why did I skip so many of these? Current event exercises. Yeah, oh yeah, it was like exercises, further reading. It was further reading and then exercises, and then I skipped those. So I just went to general exercises, and I do want just to say, like, go to, and I'm not even going to call it examples anymore because that's stressing me out. It wasn't examples, they call them exercises. Okay. And I think from what I've heard, it should change it for me here. When I come down to where I had that. Nope, it did not change it. I don't like that. Exercises. So either way, I'll be able to link out to it, and eventually I'll change it with a link once I push this to GitHub. But I have a few minutes before my meeting. Let's see. Yeah. And so in the actual exercises for chapter 1, I kind of want to just be like, you know, MEX 1.1, create, that's too many. Okay, so 3, chapter 1, create and attack tree. I'm going to keep that really simple for now. I'm not sure the best way of organizing this. A lot of it I didn't really want to do, like the attack trees. Yeah, I didn't want to do any of these actually. Yeah, so that's it for now. I'm going to fill out the rest of these examples, probably just starting on chapter 2, because they're a lot more concrete for chapter 2. Where are we? Like, just trying to give an example. So, like, consider Kirchhoff's principle, provide at least 2 arguments in favor of Kirchhoff's principle, and at least 2 arguments against Kirchhoff's principle. And so, like, for example, we'd come back here. I could probably just search, but we have Kirchhoff's principle here. So the security of the encryption scheme must depend only on the security of the key and not security of the algorithm. So provide 2 arguments in favor of that, like the fact that must depend. Anyways, let's add that to the dictionary too. I gotta head out, so I'm going to continue from here again on, oh my gosh, it's already Wednesday, so Friday. And until then, I hope to fill out more of, honestly, again, even chapter 2, I'm not that bothered. The real difficulty I'm having so far is chapter 3. And so I hope to maybe just like, keep it at like number 1 and go through them. But I hope to be able to go through chapter 3 exercises maybe before Friday or have a better outline here. And also the Zero to Production book. I want to start getting some notes, at least of the first chapter, and then start building as well. But yeah, see y'all, everybody.